Our final speaker for today of the symposium is Professor Jin Quan Yu. Professor Yu completed his Bachelor of Science degree in 1987 from East China Normal University in Shanghai, China. He finished in the top 5% on the national exam, which earned him admission into the Shanghai Institute of Organic Chemistry. And in 1988, he completed a coursework master's degree from SIOC. He then went to Guangzhou Institute of Chemistry in Guangzhou, China, and completed a Master's of Science degree in 1990 under the mentorship of Shuda Xiao. He then went to the University of Cambridge in the UK and studied under Jonathan Spencer, earning his PhD in 1999, and then stayed on as a junior research fellow at St. John's College until 2003. And during that time, he also completed postdoctoral studies at Harvard University with Professor E.J. Corey. Then from 2003 to 2004, he was a Royal Society Research Fellow at the University of Cambridge. And then in 2004, moved to Brandeis University, where he started as an assistant professor. In 2007, he moved to the Scripps Research Institute as an associate professor, and in 2010 was promoted to full professor, and just last year was named the Frank and Bertha Hupp Professor of Chemistry. Like so many of our speakers, all of our speakers for the symposium, Professor Yu has many accolades. He is a fellow of the American Association for the Advancement of Sciences, as well as a fellow of the Royal Society of Chemistry. He has numerous awards. Just to list a few of the most recent, he has received the Raymond and Beverly Sackler Prize in the Physical Sciences, as well as the ACS Cope Scholar Award, for which there'll be a symposium in his honor next month at the Northwest Regional Meeting in Corvallis. He's received the Mukayama Award from the Society of Organic Synthesis in Japan, as well as a Sloan Research Fellowship and the Camille and Henry Dreyfus New Faculty Award. I thought it was interesting looking down his CV that since his first publication in 1995 with Professor Xiao, he has published at least one, typically many more, journal articles every single year, despite changing universities, starting an assistant professorship. He clearly does not suffer any detectable induction periods. Since starting his independent career only about 8 years ago, he's published over 80 papers, many of which have been highlighted as hot papers, VIP, most accessed, or whatever the particular publisher deems their top publications. His major research thrusts have been development and application of several transformations centering around CH activation of both sp2 as well as sp3 carbons. And the reactions his group has developed take advantage of very simple, common functional groups to direct the position of CH activation, as well as ligand acceleration to achieve these transformations under mild, very practical reaction conditions. A few years ago, I was talking with a colleague mentor of mine about CH activation. What he said to me was that the problem of just activating that very strong bond has largely been solved. The more exciting question now is, what can we do with it now that we've done that? And I think we'll all agree that Professor Yu has answered that question with vigor. So, turn this over to you.
Thank you so much. Thank you. Thank you so much. Can you hear? Okay. AJ, thank you so much for your kind introduction, and I'm most grateful to, of course, to Scott and to the organizing committee for allowing me to be here, to be part of this wonderful celebration of organic chemistry. I think so far I have been, really, it's amazing. Every single talk has been a great treat to me, and let me say this one more time, congratulations to Professor Evans. Although I have not directly received a supervision from Professor Evans, but as you will see from many of my slides, our program actually are heavily influenced subconsciously or consciously by Professor Evans' chemistry and the philosophy of doing chemistry. I'm not necessarily, that of course is not necessarily too much of a credit to him, but nevertheless, that's a fact, okay? And to give you one example, in the very beginning, the proposal actually was formulated just a few meters away from his office when I was a postdoc. That was the first proposal, 2001. It was in terms of what we want to do. And the dream was to develop Evans auxiliary-like directing group for CH activation. And that, I didn't realize that would take us 12 years to finally today I will show you. I hope that Dave would agree this is getting very close to Evans auxiliary-like directing group. And then in combination with the ligand acceleration, hopefully we can do many, many chemistry. And that is actually probably main theme of my talk today. And I think it's the most fitting in this occasion. And another a few sentences I must use the time for is I would like to congratulate all the speakers for the wonderful talk. Okay, and it's really a humbling experience and almost intimidating to have to give a lecture after hearing so many wonderful sciences in the last 2 days. But I think I maybe should just take this, considering this is the best audience, right, for organic chemistry. I think I should just take this as a home game, and hopefully I will score a few 3 points tonight as well. But if you notice, actually, if I just, in case someone don't know this morning who speaks so far, is Eric Carrera, Paul Nashua, and Bill Rush, and Scott, just now. If you notice, all of them are as tall as LeBron James almost. So they basically all did a slam dunk in the basket of chemistry, right? So I have to score 3 points. But anyhow, this is the outline because it's very late and you may have to leave early, but let me make sure that this is the 3 very key messages I want you to take home if I couldn't make myself clear. The first 3 slides, I just want to focus on 3 redox chemistry for catalysis, why we chose those 3 redox chemistry, and I won't go into detail, and that's not the focus of my talk. The focus of my talk is really all about substrate. What kind of substrate you want to work with in terms of sp2, and how do you get the reactivity? And the key to that, the trick, the strategy, is to really exploiting weak coordination and then match that weak coordination with a ligand acceleration in the transition state. And that's the second part. And then I will move on to the third part, which is still very difficult, but now we're getting also there to use a weak coordination and the ligand acceleration, as I already hinted. It's basically use almost like Evans auxiliary-like directing rule, and then use a ligand to match the transition state to accelerate, and then you can do many, many reactions. And let me then emphasize one more time. There are so many problems still, despite all the efforts from not just myself, Melanie Sanford, Douglas, many great chemists in this field, especially in my generation, many young chemists are doing great stuff. But let me emphasize, despite of all those efforts, we still have so many problems in this field. And one single most important problem at the moment, at least in our mind, in my lab, is how do we discover a new ligand or new strategy that would accelerate CH activation. What I mean is by precisely lowering the transition state of the CH cleavage step to accelerate CH activation and then control the regional selectivity and control the enantiomer selectivity. And hopefully I will show you all those examples today. So up front in the very beginning, let me first give you what is the proposal in the beginning 12 years ago in Harvard, what I wrote, then I went to Cambridge to try to finish this, was to really deliver all those transformations from CH bond. You might wonder, as assistant professor to start, why you want to develop all those transformations. Actually, you just heard from Scott. As an organic chemist, you never knew. You want to make anything, right? And translate that ambitious goal of organic chemistry to developing method, meaning you have to develop make any bonds. Ideally, you want to be able to make any bonds you want because you can't predict. We have just seen Scott's beautiful talk. In many of those, sometimes you need a bromo, sometimes you need a boron even, or even directly CC coupling. So it's very important that we can turn the CH bond into many bonds. And indeed, we chose the organometallic approach instead of many other approaches are just as good. Carbene insertion, nitrogen insertion, they are all beautiful chemistry, but we decided to focus on the palladium chemistry because there are so many literature or knowledge that we can really stand on the shoulder of giants how to exploit this carbon-palladium bond. So the key really is how do we really develop a new strategy to make the C-palladium bond really well in the stereoselectivity manner and regioselective manner. So let me then be very brief before I move on to talk about the focus, the key topic, the catalysis. So the first catalysis that really caught our attention is palladium-2,4. And of course, there's no way that I'm trying to claim we invented this catalysis. And there are so many present before us, 2003, before we started. And as you can see, all this pioneering work, and there's not enough space to list all the names. And let me just highlight the new generation, Melanie Sanford and Douglas, we 3 basically started the same year. thinking about related ideas, try to exploit this catalysis that is very well established in the 1980s. And let me walk you through very quickly this catalysis. You take a very simple catalyst, palladium acetate, that's not a ligand controlled yet. You cleave the CH bond, and you generate the alkyl palladium bond or arrow palladium bond. Then you chose this interesting oxidant to oxide palladium 2 to 4 in order to trigger the reductive elimination so you can get the bond you wanted. And clearly there are two problems for this catalysis. Number one, the oxidants are too esoteric or expensive or not general, because I think I won't get into that in much detail, but let me tell you, most of the oxidant that we use are very expensive and chalcogenide type oxidant. Another problem is, even if you can do that, and then when the reductive elimination happens, the choices gets too many in a single reaction, because you have 3 ligands that now can undergo reductive elimination that will give you a mixture. Although myself, Melanie Sanford, in the beginning, we hide the 10% in the supporting formation, but that editor won't allow us to do that anymore. So we really can't do that. We really have to solve the selectivity issue. That is a huge problem. And we came up with this idea using a bystanding oxidant that you can really oxidize the palladium but not involved in the reductive elimination. But still, it's very early stage, that idea. Nonetheless, I'm very pleased to tell you, just before this conference, we finally succeeded in my opinion, maybe so far, the dream catalysis for me, for us. We have been chasing this reaction for now 12 years, palladium 2,4 practical reaction using iodine as the only oxidant, crystal iodine. And then to turn this over, as you can imagine, if you put iodine there, it's great. It's a very safe and cheap oxidant. But immediately you run into trouble because you're going to form palladium iodide, which is a very nice crystal, brown crystal, like sugar, but it's dead, not reactive. However, with this, as I already hinted, this Evans auxiliary-like directing group, as we clearly stated in our recent 3 papers, that's the idea. But of course, you need a ligand as well, but I can't show you the ligand structure before the second part of my talk. But let me emphasize, it's just very simple iodine, and you can use 0.5 mole palladium. And at the same time, using this auxiliary, we also solved all those dream extremely valuable heterocycle chemistry we have never been able to do. And the principle behind this reactivity I will tell you about in the second part of my talk, but this is just tell you the catalysis. So far, I believe the first palladium 2,4 catalysis, finally we can scale up to kilos. And this is in close collaboration in BMS, and this has worked in numerous drug discovery projects. Many of them is a late stage radio labeling, iodine radio labeling, fluorine labeling, and tritiol labeling strategy application. It really works with a very complex setting. And the second catalysis I want to share with you is this palladium 02 catalysis. I have to say, this catalysis is the most established catalysis, most well-developed catalysis in the 1980s. And to be honest, for a long time, I had a little confidence in working on this catalysis for a reason I will tell you immediately why we did not jump on this catalysis for a long time. Let me walk you through. The first step is almost like a Hecker reaction, oxidative addition from palladium 0, then you generate this palladium alkyl or arrow species, then you react with CH bond. If this CH bond is sp2, that just mimics the Hecker reaction. Basically, sometimes the aromatic ring double bond is broken. So basically, you're doing electrophilic Hecker reaction. But the beauty of this catalysis is you don't need to worry about the turnover because it's a Hecker reaction in terms of redox chemistry. So it's beautiful in terms of, in the long term, in terms of practical catalysis. But there are huge problems if you really want to do CH activation. Why? Number one, when the CH activation happens, the palladium is not an innocent catalyst. Basically, you have to have this particular ligand that is required for the oxidative addition. You also already installed on the palladium of one of the coupling partner. Basically, what you're doing is, before the CH activation happens, you want the palladium to run a 10-meter spring in 100 meters, but they already carry 20 bags, 20 kilo bags. They don't have energy anymore. And it's very difficult to manipulate that species because you don't have enough coordination side either to design the catalyst as you wish. So I thought this will be a tremendous problem and limitation. You can never do maybe sp3 CH activation. Indeed, by calculation, based on current mechanism, there's not enough coordination side to do intermolecular sp3 CH activation. So basically, I have written this off. But turns out the student proved me totally wrong. Okay, the first year student was able to show me so far the 2 examples, and this is the extraordinary example. I was totally astonished by a first year student just arrived to show me that he can run this reaction. But again, this is based on the magic Evans auxiliary-like directing group. And the principle behind that I'll show you in a moment, okay? And what happened, if you look at this intermediate, the platinum-0 oxidative insert into the carbon-bromo bond, forming this intermediate you can see monitored by NMR. And it's remarkable that this species was able to coordinate to this auxiliary and cleave the CH bond intermolecularly. And that really invoked the transition state. Palladium has to be 5 coordination. And that calculation paper will come out in JAX very soon. So it's a very unique transition state. The palladium has 5 coordinate, but it's a very long bond. The phosphine has a very long bond to really allow the coordination to come in. It's very interesting. But that's, again, the second catalysis. And finally, my favorite catalysis, to a great extent, I guess this is the catalyst that we can claim that we invented to some extent for the cross-coupling reaction. You take a CH bond, you cleave the CH bond, you generate palladium-2. Now you are almost in Suzuki coupling, but one step before that. Instead of reacting with other electrophile, we react with organometallic reagent to make the diaryl bearing palladium, and then reductionation give you a CC bond. The beauty of this catalysis are twofold. Number one, you can then potentially use air. As you can see here, I will show you today, we can use air with the help from ligand to turn this over, right? Shannon Starr has shown beautifully, use air, you can reoxidize palladium-0 back to palladium-2. And the second advantage is you can somehow, because when the palladium cleaves the CH bond, it's a free catalyst, so you can pretty much throw in any nucleophile in principle. And as Scott has just demonstrated, you can throw in the araboronic acid, right? And so that is very interesting because for the first time, we made a connection between CH activation, which is usually very narrow scope. Now, suddenly you open a door connection to Suzuki coupling, which is very easy for the medicinal chemist to think about new disconnection. You don't need to think about it, but it's already known. So we really just join them together without creating a new disconnection, instead of just helping to connect them. So that is why we are very much we like this catalysis. And let me show you one classic example that has been used by Glaxo Wellcome for drug discovery. So you're taking this substrate, again I'll explain why we designed this auxiliary. Taking this substrate, you can do a sp3 cross coupling, almost like a magic, to making this library of this molecule. And this turns out to be a drug candidate for a huge library generation, one step. In 1 week, you can generate several hundred, very easy. So that's the third catalysis. But let me then go back to tell you about the second part of my talk. What kind of substrate we want to work on? How did we choose those substrates that apparently in the beginning is a huge risk? If you chose some other substrate, you already knew you can have CH activation, 2-phenylpyridine, imine directing, you know it's going to work to some extent. But so why we chose those substrates that didn't look like it's going to work? If you look at those 3 reactions, in my opinion, despite we have hundreds of reactions in the history, right? In my opinion, these are the 3 kings of the asymmetric catalysis. Why is that is the case? Why this still to date are the most widely used reaction in medicinal chemistry and in synthetic chemistry? The reason is very simple. Because for 2 reasons. The substrates are readily available not only in quantity, but also in diversity. You can buy a lot of analogs, and therefore you can plan many synthetic applications. Number 2, the product. The product can be mapped into a major class of product used for functional material. In this case, amino acid. In this case, Barry was thinking about sugar. In this case, David Evans, of course, revolutionized the polyketide synthesis. It's very obvious why those 3 reactions are the kings in synthetic chemistry, right? So here, just repeating the 2 sentences. So having really have a strong belief in these 3 reactions, there was no choice but for us to think about what kind of substrate to work with in the beginning. We decided really to focus on these 4 classes: carboxylic acid, amine, alcohol, aliphatic acid. And because all of this you can buy in 100 grams and 500 analogs easily from Aldrich. And that fits the criteria, number 1. Number 2, we then think about another dimension, because there's another problem. Because in the David Evans chemistry, you don't need to think about the distance because it's controlled. You have one position that is guaranteed. But in this case, you could end up with many CH bonds. So we really have to control the distance, because you never know what kind of substrate you're working with, what kind of structure you want to make. In this case, when you move this function away, then you have a distance problem. This is already difficult, weak coordinating, but then we want to do is control the distance as well, 7, 6, 7, 8 bond, we want to do all of those control. And you might ask, what about another 12 bonds away? Actually, that's less useful. Although I will show you we can do 15 bonds away today, but it's less useful because if you move away from there, then you hit another function in organic synthesis. You can use another one. You don't need to chase all the way to the end. Okay. So let me explain to you one more time why the distance is very important in synthetic in CH activation. Let's say you want to make isoindolin. As we develop the chemistry, we do CH activation, we couple to a Heck olefin reaction, we make isoindolin. What about if you want to make indolin? We have developed recently, just published organic letter, we can develop a 5-membrane cyclization indolin. That's another distance. What about if you want to make a quinoline? Then you need one more carbon, right? And that yield is still 50 to 60s. Still very difficult, but that illustrates why the distance is so important. We need ligands to really promote the very remote interaction. It's almost like you have a girlfriend in Shanghai, you want to get a kiss. Very difficult. It's far away, right? So you really need some help here, and that is what I'm going to show you. It's going to happen actually. Okay, so again, as I said, in many things that we do, we stand on the shoulder of giant. And in this case, it's no exceptional. Both myself, Melanie Sanford Douglas, we are all standing on the shoulder of giant. And those are the beautiful examples. My hero in Britain, he's a giant organometallic chemist in Leeds, and he discovered this reaction, imine-directed palladation. This is another one, and this is from Japan. Beautiful chemistry, and I should also mention in the 1980s, they have also shown oxazolin can do CH activation, but I don't have enough space. But let me tell you what we're thinking. Well, I already told you, when I was writing proposal in Harvard, I was influenced by Evans auxiliary. And of course, I write a proposal about it, how to do it. But I knew it's not going to work immediately. So what do we think is missing? Maybe in order to understand how the CH activation works, what's the structure? What's the transition state? If you take all this paper out, there's no information. What's the structure in the transition state? And what's the conformation from organic chemistry perspective? So we thought, in order to get all those information, to peek into the detail of the transition state, what is missing? If you think about Evans auxiliary, what's missing? Stereochemistry. We need that. So we designed this chemistry, although this took us a long time, although we had the reactivity very quickly in Cambridge 2003, we had those crystal structure, but we never had a crystal structure that have both chiral center on the ring, on the auxiliary, and on the substrate. Because this crystal is extremely elusive, it's hydrophobic, these really melt in hexane. And in the end, after 80 years in Scripps, we finally got this crystal structure. Basically, I told Ramesh Giri, my first student in Cambridge, I told him, if you get this crystal structure, that's the last chapter of your thesis. And the next week, he got a crystal. And I wondered how he got it. He told me how he got this crystal is to dissolve this structure in 1 gram and saturate them in hexane and then put them on top of a liquid nitrogen, and this came out as a huge crystal, single crystal hexagon, actually very big crystal, and that just tells you a little bit of pressure, like a Bill Rush, a little bit of pressure, just right amount, it really works. So if you look at this crystal structure, then we start to have all the data. We start to study NMR. We knew this is a solution structure because we can do this NOE, we can do NMR. We are very confident this is by mass, it's in solution, it's a solid state, and you can now start to see the conformation. You start to correlate the sterics between this auxiliary and the substrate and try to do kinetics, try to correlate the reaction rate of the CH activation and the conformation. And I will cut a long story short to tell you what we discovered. What we discovered is the reaction rate has nothing to do with the coordination strength. So that means you don't need a strong coordination. The bond doesn't matter here, coordination strength. Secondly, it really correlates really well to the conformation. Whenever you have the CH bond here, it's approximately being coplanar to the square plane of the palladium acetate, then you get very great reactivity. To give you one example, if you remove this tetrabutyl and put in the isopropyl, very small change, the bonds start to rotate and you get away from the coplanarity and almost no reaction at 80 degrees. But if you have 2-tetrabutyl, this reaction couldn't stop at 0 degree. You can do this reaction in fridge. So that tells you the key for the reactivity is the conformation controlled. So we got very excited. So now the next question, actually this is afterwards, this is more recent than Ken Hogg did a lot of beautiful study to confirm that the distereoselectivity what we obtain can be predicted by this model. The palladium acetate and the CH bond has to be lined up in all those transformations, indeed. So that's very interesting. But we made a bold hypothesis with very limited information. Sometimes it's, I guess, sometimes it's good to be ignorant. We didn't know enough, but we proposed anyway. So we went forward. The hypothesis was, can we mimic this structure but without using oxazoline? Oxazoline is a nightmare, and there's nothing to speak of in terms of practicality, okay? We knew that, and that's not what we wanted. We didn't want to develop that as a synthetic chemistry. We were only using that to really peek into the transition state, and then we hope to develop like Evans auxiliary. That was the idea, okay? So once we look at this, we thought, okay, so the key is to construct that assembly, the conformation, but without using the oxazoline, can we do carboxylic acid? And as you know, this is what's going to happen, the eta-2 coordination. And you know there's a possibility to form this so-called anti-lone pair. The anti-lone pair could coordinate the palladium, but you can see that's going to be fighting. And that's why the reactivity is very bad, because you're equilibrium. And that's the major species anyway. However, by accident, one of my mentor's mentor, Jim Staunton, when I was doing biochemistry in Cambridge, Jim Staunton was my mentor's mentor, basically. He accidentally drew my attention to this kind of crystal structure because he was very big on sodium coordinate to polypeptide, actually doing mass analysis, and I was helping him give some free help. So sometimes as a student, if some senior asks you to get some help, you should help them. You really always benefit. And I was doing some work for him for free, basically. But by accident, I noticed there's a crystal structure in Cambridge database that has a sodium coordinate to the carboxylic acid. As a student, at that time I was not a student anymore, but as a junior scientist, I was very intrigued by this structure. So naively, I thought, maybe this is the Evans auxiliary. Can we use that as an Evans auxiliary to lock up the syn lone pair and then ask the palladium 1% catalytically come in to coordinate to the anti-lone pair? And as you know, Tony Kirby, another mentor of me, and Ken Hogg has studied extensively the energy of the E-lone pair and the E-lone pair and the syn lone pair in 1980s. Although they didn't say why they are studying it, but it's very helpful for me. So if the palladium indeed can coordinate to this lone pair, then you can imagine this structure would resemble the left-hand side very much. Maybe we're in business. So of course, that's a great idea, but it's always very hard to persuade a student to stay on that project for 3 or 4 years without getting any result. So in this case, we had to change a few students, and eventually we landed on Tyson. And the way we call him Tyson, as you can imagine, Tyson has a very strong teeth, can bite into CH bond, right? As you know. So his name is Tyson, and this is what happened. So if you mix the substrate with palladium acetate, nothing happens. And we screened extensively, heat them by temperature, whatever you do. And you see beautiful chemistry discovered by Andy Myers, of course, decarboxylation, which is great chemistry, but that's not what we wanted. So if you like cooking, just walk to the kitchen and get 1 spoon table salt, and you dump into your reaction. Quantitatively, you can isolate this intermediate. For the first time, in my opinion, physically prove that a weak coordination indeed can direct palladium insertion into CH bond. And this is fundamentally different, mechanistically and redox chemistry different to Marias chemistry, okay? And in a moment you will see, because then the scope is different. So you might wonder, what took us so long for several years to discover this chemistry? It turns out, this looks like a palladium black, except it's gray. And they form a very thin film in the glassware wall. So every time we wash them down to the sink, we miss them for a long time. And eventually, we believed this hypothesis so much, we couldn't believe this didn't work. And eventually, we decided to break the glass into pieces and check everything and dissolve them in DMSO, and we actually got a pure compound. It was this compound without any purification, because that's the only solvent that this would dissolve. And we got a quick structure later, of course. Now, there's a big question. Looks like we can use weak coordination to direct CH activation as an auxiliary, but can we do catalysis? If you look at this diagram, what we have been doing in the last 50 years, we have been doing a strong coordination direct to the CH activation through relatively low transition state. Then you drop into this thermodynamic stable complex, as George Whiteside has actually been been pioneering working in this in the 1960s. Many organic chemists played with it, and inorganic chemists, of course, collected thousands of the structures. But they are too stable, and you can imagine this mountain is very high in terms of functionalism, right? And some people may argue that I'm exaggerating by drawing this step so high transition state. But remember, if you're a student, before you discover the reaction, that's like Everest mountain, okay? It's very high before you discover the right condition. After you have the right condition, of course, this can drop. So that is a huge problem. And number one. Number two, even if you get the product, this is not going to turn over very well. And that's in the beginning. All of our paper in the first 5 years, turnover of 100 is the best. 20 most of the time. And actually many of them are 10. Because this product has a pyridine, oxazolone, they are going to kill you in terms of turn off rate. So the off rate is very, very bad. And if you are familiar with enzyme catalysis, they never do that. They always do shallow well catalysis very fast, moving forward. So it's very encouraging. Now we can use a weak coordination to push them up. Hopefully we can do the catalysis better. Is that the case? It turns out to be very, very much the case and very easy after that. Take this intermediate, pretty much we developed anything that we wanted within 2 years. And let me highlight a few my favorite transformation. Suzuki coupling, I already said. Hydroxylation here, very unique, use air. Just bubble air in, you get a hydroxylate. And that's also the first time that you can do that with palladium. And maybe here there was a few other lists. I didn't have time, but I already said iodination. That also worked with simple iodine. So it's very interesting in terms of weak coordination promoting catalysis. But that is just the beginning. What is really the big advantage is the distance. Because this is already weak coordination, the conditions we develop for those functionalization is just require a little bit of weak coordination. So the distance doesn't matter as much. So we move away the distance, we still can do it. Even hydrosalamic acid. And remember, that's not a one substrate, that's 500 hydrosalamic acid you can buy. And that really expands so-called synthetic genetic code if you want to, if you wish, as a synthesis. And of course, at the moment, we are finishing, we just published ether. That's the best example to support that indeed the weak coordination is really sufficient enough. Ether can do it. And of course, wiring amide, we just finished a full paper as well. And alcohol, we also published it already. So that's very promising. And if you're still not convinced, we have just got this reaction, just submitted actually. We have shown that by looking at this weak coordinating subject, you can watch the CH aviation going backwards and forwards, catalytically incorporate a deuterium into it. And that has never been shown through cyclomethylation because if you use the 2-phenylpyridine, you get no deuterium incorporation. And this is in a very simple setting, less complex setting, a good control experiment to show you, indeed, the weak coordination is very reactive in CH aviation and very reactive in reacting with an electrophile. And of course, it's questionable whether the deuterium, how did the deuterium get in with a proton? Is that palladium 2 and 4? I doubt. I think in many of the we claim palladium 2,4 could be simple sigma bond metathesis, just electrophilic cleavage. And this is a great evidence that you can quantitatively get this deuterium incorporate into this condition. It's a very interesting mechanistic piece of information. And let me show you this kind of weak coordination indeed is useful in synthesis. I will just select a handful of example from Japan. From Harvard, and this Andy Myers wrote me a letter. They have used this hydroxylation in the tetracycline, the precursor synthesis. Actually, he told me specifically it's 20-gram scale, and this is 20-gram scale, and this is functional. That's also 20-gram scale in the support information. And of course, my colleague Phil Barron just finished the synthesis using both steps. At the final step, using our ligand accelerated cross-coupling, I will show you in a moment, and ligand accelerated hydroxylation to install this two function group. And you may think it is trivial. But if you have to deal with these two functions in the beginning, that could cause you a lot of trouble because of the pattern, because of the protection, deprotection. But now you can do that in the final step. And I'll just give you one representative example from medicinal chemistry. This is a very interesting scaffold that's finished in the library by BMS. And they made a library using this cross-coupling reaction. Okay? And of course, Pfizer has also caught up this. They published together with us, try to develop a library of the weak coordinating direct CH functionalization. In this case, it's sulfonamide. But again, the idea of the directing group is the same. It's the same auxiliary that I will explain to you in a moment, how we designed that. But before I show you the detail of the sp3 CH bond and how we designed the auxiliary, I actually want to show you the sp2 CH aviation still need a push. That is a ligand. How do we develop a ligand then to match the weak coordination to further lower the transition state? okay? And this is the assay we have to have. Without the assay, how do you discover ligand? You need the assay that will tell you that the ligand is involved in the transition state. And this is what we did. We set up the substrate, and we tried to find the ligand that would influence the stereochemistry here. If we can get 95% EE, the chances for the ligand to be involved in the transition state is pretty good. Not 100%, but pretty good. And that's what we can do. So we set up this assay and start to screen. And the first challenge, of course, you can imagine, is how do we get the ligand and the substrate to dance in the dancing party together whole night without exchanging the dancing partner. That's not easy, because the two substrate would coordinate to the palladium, or the two ligand would coordinate to the palladium. And remember, we cannot touch the two anion here, because that's what we needed. In the moment, you will see in the computation study why the two anion is required. And what you really hope to achieve is one ligand really loves the one substrate. They're inviting each other all the time and dance whole night without exchange partner with anybody else. And then finally, once you assemble that, you still have one more hurdle. That is, the conformation, remember, has to be right. The ligand has to influence the conformation of the substrate so that the CH bond and the palladium acetate has to be minimum dihedral angle, if the undergraduate would know that, within 20 degrees, and then you get a perfect catalysis, okay? That is the dream. And I have to cut a long story short here, but as you can see, this again actually is so related to David Evans' ligand design, and that is again accidental, very interesting story. I don't have time to tell you, but let me tell you the key story. We discovered this very simple ligand, amino acid backbone, through this bis-dentate coordinate, but the key discovery is this monodentate coordination, the mono protection here. That is very important. And let me walk you through this design, okay? So the bis-dentate is very important because that guarantees you very high fidelity in terms of coordination. But at the same time, they prevent the second ligand to come in, because if you want to do the bis-dentate twice, that is actually extremely unstable through electronics transit effect and through steric effect. So you can only have one ligand. So now that opens the vacant side to inviting the substrate to come in. So that's perfect. And then through the transit effect, we were also very happy, very lucky I should say. The substrate sigma donor would always come in from behind, not from front. If it coming from both front and behind, then we were totally in trouble, because you would get racemic, right? And then finally, how did we control the stereochemistry? The stereochemistry is completed through the we call atomic gilding, and as we cited here, David, I think, came up with the idea of atomic gilding through conformation, controlling the stereochemistry of each atom. Instead of, you don't have a face here, you don't have a ray phase, a side phase. You have to control each atom, the stereochemistry. So the isobutyl, almost like LeBron James, very aggressive. They would elbow down whoever is next door, and the Bach is pushed down, and that Bach then pushes the transition state steric hindered substitution up. That controls the potential CHI transition state. And this is not transition state, but you will see in a moment. But let me show you the result first. The result was great. 95 E for the first time. Big celebration in our lab, because I know this subject is ugly. We had to put in all the method to weaken the coordination. The coordination here is very weak because the sterics, we want it, so you can do catalysis. But it's the principle. We show this idea definitely works. Then takes another 2 years, we were able to expand this to weak coordination, sodium as an auxiliary. Now we can do enantioselective selective CH-activation. Furthermore, we can do cyclopropane to show you. And that again, using this, I call it Evans auxiliary ligand directing group to do this enantioselective selective CH cross-coupling reaction, set up a 2 chiral center in one part. And the beauty is you can make a library. You can make 500 of them, okay? And of course, if any chemistry is good, someone else is going to use it. If nobody uses it, that's going to be a problem. But in this case, we have one of my former students just published a beautiful paper using this ligand to do lactonization. And you see, that's a 95 EE. And another first-year student from my lab is trying to develop iodination technology actually would complement with John Elman's chemistry. If you go to industry, make color aiming, John Elman is really the Bible of chemistry, okay? It really works, large scale. So we hope to develop a different approach to complement John Elman's chemistry. As you can see, I'm sure some of the synthetic chemists must be worried about how do you remove this triphamide. It turns out we developed a very nice room temperature protection strategy based on Dan Heiser's early chemistry. And I don't have time to show you, but it's very practical. We can install this and remove it. It's room temperature. The ligand is a magic, the weak coordinate is a magic, and this iodine is a magic. So you don't have background reaction. If you use phenylalkyl iodine, you can cause a lot of trouble. But now, with a complex setting, and you can do this room temperature iodination. And let me tell you, sp3 also on the way, also works. So you really form a very nice complementary choices for John Elman's chemistry, which will be great. I haven't communicated with John yet, but definitely I'm going to call him very soon. I'm sure he'll be very happy. I have always been inspired by his chemistry. And of course, finally, if you look at this ligand, that's a very famous backbone ferrocene chiral base and for organocatalysis, but it's not easy to make. But now, by another group from China, SIOC, one of my friends, was able to using our ligand and Suzuki coupling, making a library of this ligand by just one step in enantioselectivity. And that again shows you the power of this kind of chemistry. And I'm very afraid of talking about mechanism, but I think I don't want to miss the opportunity to be challenged by so many great organic chemists. I will do it anyway. So this is what we knew. We have the precursor here. And we didn't know what's going on, and that is apparently not stable. And we got this intermediate, CH insertion intermediate. But what's happening here? By computational study, it turns out this NH bond is not stable. Immediately activated to generate this species. And that's perfect, because that kicks out the acetate and generate this vacant side, which is ready to do agostic interaction with this carbon center here. And then this carbamate is not innocent, as we thought. The carbamate actually serves as an internal Lewis base to pull off the CH bond to accelerate the CH activation, to generate the palladate. And this palladate, unfortunately, we could not isolate so far. But you never know with a new student. We try to isolate this, okay? And we rearrange this back to this guy, which is thermodynamically stable, and we were able to isolate. But what is amazing is this intermediate was able to do all kinds of transmetallation cross-coupling without using sodium methoxide like Suzuki needed. Otherwise, we would have been big trouble. We would need sodium methoxide. But this ligand allows you to do pretty much everything. And I don't have time to show you all the transformation, but let me show you the most important point. That is the transition state I keep talking about. Did we really accelerate? Indeed. With this ligand, we can accelerate this reaction to 20 minutes, and you can imagine there's no other reaction can do this, CH reaction 20 minutes. And you can drop the catalyst loading to 0.2 mole%. And if you scale this up, you can go down to 0.01, because when you scale up, actually it's easier. Okay, but we in a reaction flask for 5 gram scale, actually for 20 gram scale for organic sensor prep, we did 0.2 mole%. And we're submitting that soon by Kiri Ingo, who was a wonderful student from Michigan. Actually, he was educated by Melanie Sanford and sent it to me. Great student. And he is one of the best marathon runner in the Los Angeles area, but he admitted he would never beat this timing, 20 minutes for marathon. So it's very, very, just give you the perspective how fast this reaction is. And of course, you might argue there are so many steps. Are we really controlling the CH reaction step? And Donna did a very beautiful study, kinetics. As you can see, first order in catalyst, 0 order in substrate. That tells you clearly it's the weak coordination is efficient, it's enough. It's a 0 order already in substrate. That means the weak coordination is really good enough to do the catalysis. And of course, as I already said in the very beginning, when we make the product, we already knew what kind of structure we want to map onto. And in this case, we want to map onto this tetranol, because tetranol is a very interesting class of synthetic building block. And indeed, we made all those natural product or part of a natural product using our chemistry. In all those cases, we have done in gram scale or 20 gram scale in one case, and to control the regional selectivity by using a ligand. As you can see, there was an issue here, regional selectivity issue, and using the ligand, we can control, not very well, but 5 to 1, 10 to 1, depending the case, okay? So, and in the end of the day, this is to this audience, I do want to show you this chemistry can also be used for total synthesis. And I remember yesterday a speaker mentioned, Dave mentioned, if you look at this molecule, the first thing is, can you break into 2 pieces, convergency? And we did. We break this molecule in 2 pieces and then worry about the chemistry, whatever we can do. And you can see what we needed to do is to put the 2 pieces together. But that would really be very challenging, because this Carboxylic acid group, the dihedral angle is a little bit wrong. It's 53 away from the CH, 53 degree away from the CH bond. And this guy is very, very fragile, this chiral center. If you try to do a Hecker reaction, that's not going to survive. And to put a bromine there, it will take you many, many steps. So the CH ablation really is the only way to go. But using this ligand, magic ligand, we were able to pull this off in the last but second step to do this chemistry. And I have to tell you, to deprotect this methyl group, we need a lot of help from John Elman, who finished the synthesis before us, of course, and he was very generous, helped us to deprotect this and finish the synthesis, okay? But the point, it didn't stop here. The reason is, the reason we want to do this disconnection is to hopefully, by providing a new disconnection, and you open a new door for discovery of a new chemistry. And the new challenge is, now we knew we can make the two pieces together, we can put the two pieces together. Can we make these pieces even better? This one we can do it very easily, but what about this one? We then develop another CH activation chemistry by using hydroxyl-directed CH activation, one step forming this benzofurane ring, and that is very interesting. And then when we look at this, we need to construct this bond asymmetrically. Can we do another CH activation enantioselectively in collaboration with Hugh Davis? This is 70% yield, but 80% EE. Now we're doing three-step synthesis up to here to finish this scaffold. And indeed, this synthesis has already been amplified and used by Professor Ghosh in Purdue for anti-HIV study in the program. And I should mention, you see Erica Carella's study, beautiful, using Justin's chemistry, right? Beautiful chemistry as well. The same principle, basically. But here, just to show you three different types of CH activation together can even get better benefit in terms of simplify the synthesis. And let me then summarize what I have done so far in the second part. Basically, I think we made a great stride in terms of a weak coordinating directing group to control the CH activation. What we cannot do yet is, what about those CH bonds that you cannot direct? What are you going to do with it? It turns out, in all those subjects, each subject has its unique problem. And my strategy, our strategy, is not trying to dream a God catalyst that would take care of all the subjects. Instead, we're going to divide those four problems into four classes. And we developed the four different catalysts for all those subjects and to solve those problems. And so far, we have catalysts for each of this, but some of them you didn't see yet. But this one we published already. I will show you in a moment. And this one I don't have time, but that was inspired actually by Forrest Mike's chemistry here in this university. Was inspired by one of his mechanistic study, and we designed a catalyst, platinum-4 catalyst, to control the para-selective chemistry. And the pyridine, we used a very interesting trans-effect ligand to control the C3. But what is very interesting is, what about in the drug molecule, you have a pyridine like this, and you know the pyridine will take you to that ortho position. But what about if you don't want that? You want another weak coordinating directing group, and there's no way you can get that to work. But it turns out that is possible. If you design a ligand that doesn't like the strong coordination, they match the weak coordination kinetically, and it turns out we can have absolute control the top CH bond or the bottom CH bond, depending what ligand you use. And that's a huge problem for medicinal chemistry. We have been bogged by many, many medicinal chemists. And finally, we will have a paper coming out very soon that we can deal with this situation as well. So you can really have side selectivity in CH activation. But let me tell you one more challenge, even more difficult. What about if your function group is far away, as I already alluded in the beginning, but the CH bond is very awkward corner. It's hidden in this corner. And the biggest problem here is all those CH bonds now are equivalent. They are like brothers and sisters in terms of electronic effect. Remember, this is electron rich center. That's electron rich center here as well, but not here. Here, this is too far away to distinguish them. And then if you try to design a directing group, that is hard, because this is a cyclophane transition state, very hard to assemble catalytically. But as a synthetic chemist, as Scott just showed you, you never know what we wanted. Maybe we want those substrate to somehow, we just want to break the CH bond against the electrophilic bromination, against electrophilic bromination here, matter, here is para, and maybe even in this case, the carboxylic acid somewhere else, in another part of the natural product. How do you recognize the structural pattern and design a system that in a controllable way, predictable way, to control the side selectivity? And that is what we want to do. And let me show you first example. using this we call mutually repulsive ligand, they form this equilibrium that would invite this electron deficient ring and cleave the CH bond, do the non-directed CH olefination. But let me tell you, this catalysis is just beginning. It's not efficient enough for practical application at all. But I think what is most interesting is this one. Turns out we solved this one actually earlier, faster. Is the remote metal CH activation. If you think about so far, what we have been doing is all inspired by lithiation chemistry. Peter Beek and Sneakers wrote beautiful review on how to assemble the cyclic lithiation transition state, of course. But now what we are asking is cyclophane structure. Can you do that? And of course, there's no way you can tell your student to do that. So instead, what I told them is to forget about this molecule as a single molecule transition state. Instead, think about the molecule substrate as a little fish, and the palladium catalyst on another little fish. Can you somehow put in these two fish in a small pond and let them swim randomly, and maybe they will bump into each other, and maybe they get head cut off or get tail cut off, depending how the catalyst and ligand controls. That was the basic idea. I know it's crazy, but maybe this idea is wrong, but it worked, and let me show you how it works. So to test this idea in the reaction flask, we designed this template, which is not practical yet. So the idea is very simple. You keep the template flat. You have the red flat. Remember the dihedral angle, right? We try to maintain the dihedral angle minimum. And then we install the sterics here, two alkyl group, very bulky. You're pushing the substrate and the catalyst potentially right into the quadrant 4. If you remember the high school math, 1, 2, 3, 4. That's the quadrant 4. That's the small pond of the fish pond. So now you hope the palladium might talk to the CH bond, but they talk to the wrong CH bond. They keep talking to the ortho CH bond because they usually bend over. Then we had to really engineer a linear coordination nitride. As you know, nitride is end-on coordination. So basically you engineer this 1 carbon, 2 carbon, nitrogen, palladium 3 as a very rigid rod, so they cannot bend. They are very rigid like a machine, like a robot, okay? Like a move like this. So they have to hit this metal CH bond. That's how, at least that's how I explain to my students. But of course, it's very hard to convince them. And I have to tell you, many postdocs quit this project. But usually they got back because we did have a crystal structure of this in the lab. Every time when they want to quit, I just show them the crystal structure. It looks so promising. And usually they are convinced and they come back to work. And after 3 years, finally, we were able to deliver this transformation. Indeed, very selective olefination. And let me show you the substrate table. We have never had such a broad substrate table because, for instance, in this disubstituted olefin, trisubstituted olefin, there was no way we can do that before. Now we can even control the stereochemistry. From cis we get trans, from trans we get cis. So it's very interesting chemistry because the weak coordination is coordinated, and when they need, they go away to give the place to the substrate, so for the olefin to coordinate. So it's very powerful and effective. But of course, that's just a test of the principle. That's not practical yet. To make this more practical, we actually bought this from Aldrich. Is the Aldrich people here? We like Aldrich. So this is from Aldrich. So this is very close to Evans auxiliary in my opinion, because the condition we use to remove this actually mimics Evans auxiliary removal. And to install this is also very easy. So what do we call this? The molecular U-turn, inspired by the first project. As you can imagine, the deal here, the trick here, is to use the amide bond to do, and the CN bond to do a molecular U-turn. It goes away and it comes back and cut the CH bond. And Julius Riebeck told me he once thought about the molecular U-turn in his supermolecular chemistry, actually. When I showed him this chemistry, he was very happy. And certainly we will dedicate one paper soon to him for his inspiration. But the chemistry works really well, as I told you. Even you block this ortho 2 methyl group, it still works. That's kind of amazing, because you block the 2 CH bond, they can still do a U-turn and hit from the top and cut the CH bond. Very efficient. And this is just the beginning. Let me show you what's happening. This is BMS collaboration to make unusual amino acid for peptide drugs. And this is the next on the paper. This one just came out in JACS. We were able to deliver a very simple template, ester linkage, that we can now deliver unusual metal selectivity. As you can see, if you want to do bromination, whatever, you will get a mixture of ortho or para. But now you get a metal. And if you take this very complex structure, you can hit both ortho and metal depending how we want to control that using our auxiliary. But what is, here you go. This is the result. You can do both ortho and metal. Okay, and many of those are drug molecule actually we did in this paper. But what is most exciting is aiming also works. We can make a simple molecular U-turn to cut the metal position of the amine, even heterocycle. And this actually, we are supposed to be collaborating with Mobasaki in finishing a total synthesis, but unfortunately, he leads some other transformation we cannot do. But at the moment, we can only do olefination and oxidation, hydroxylation. So basically, using that template, amide linkage, we can cut the CH bond and install hydroxyl or double bond olefination. And that is very interesting for medicinal chemistry if you want to install heterocycle in a unique way, because that position is very hard to reach, actually. So that's all about my second part. How much time do I have? Do I have still, I started later? I have 15 minutes? Okay, I can finish. My third part is very short, okay? My third part is about sp3 CH radiation. Now it comes to Evans auxiliary. The idea, this is actually exactly my proposal in the very beginning in Harvard when we wrote this proposal. We want to take the pivatic acid, basically, do Suzuki coupling, and then do another two-step in anti-selectivity to make a quaternary carbon center. Basically, we want to provide a new tool for the medicinal chemistry to make a library just like a Suzuki coupling, but make flat on, to help you to build three-dimensional molecule. Because I don't want script to people to think script is flat like Munich. We also want to do some three-dimensional chemistry, but obviously this is very difficult because you need a ligand, you need an auxiliary to do this really well. So we started with using just potassium auxiliary, and that did not work very well. And that worked out 38% yield, which is kind of amazing. It did work, but the yield is very low. Then we were inspired by Derek Barton, who invented this as a protecting group, right? For ester protecting group. But we used this to mimic the carboxy acid, but tune the pKa. If you're familiar with David Evans' pKa, that was my favorite reading in Harvard. It's every day look at the pKa, cannot remember it. And I think it turns out David Evans' pKa doesn't have this one. We had to do some computation study to check what is the pKa. And the pKa is really a little bit more basic than a carboxy acid. So that's good. That's exactly what we're looking for. We are looking for weak coordination, but a little bit more loose basic. So to compete with the side reaction, the homocoupling reaction, so the palladium will grab this better, but not too much better. Too better is bad for catalysis. And indeed, this is the magic, 80% yield, sp3 coupling. And this direct group, so far, for sp2 CH bond, for sp3 CH bond, this is not the best. For sp2, this is by far the best directing group because they work with rhodium-3, ruthenium-2 in water in minus 20 degree. This is a beautiful chemistry by Tom Lewis, by Kramer. They published this paper in minus 20 degree using this kind of directing group. Quite amazing. In our case, we have to 50 degree, but we can also do room temperature. If it's 48 hours, we can do room temperature as well. So it's very powerful directing group. But it turns out it's not very good for sp3 because if we try to do sp3, we need a quaternary carbon center, and that is a limitation. And in this area, whenever you publish a paper, the next day you are not so excited because you knew it's going to be another limitation. And the limitation is quaternary carbon center. If you have alpha hydrogen, it's too acidic. And that acidic CH bond, I believe, is rotating over to have hydrogen bonding interaction with the palladium acetate, and that locks away the preferred transition state and kills the reactivity. So how do we do that? We engineered extensively, but here I only tell you one result, one directing group. Finally, we were able to hit, after 12 years, we call this Evans auxiliary-like directing group, basically auxiliary, that is very cheap. You see the price? We can do this chemistry. Take a chiarosensol, we can hit it with anything, and we can do the CC bond, make a unique quaternary carbon center. If you remember, the why Evans chemistry is useful, I forgot to mention, is not only what are the 2 points, but also the third point is the transformation. Not only doing one transformation, you can do aldo, you can do alkyl, you can do today, Bill Rush showed beautifully, you can do many chemistry, right? And we want to do the same. We want to do many transformations. But now, intellectually, interesting point is, what happened? Why this direct group is so good? Well, the first thing we have to understand is the coordination structure. If you check John Hardwick and Buckhorst's literature, they will tell you, and indeed they have evidence, that the palladium is coordinated to this amide nitrogen, and that's how they do Buckhorst-Hardwick amination, of course, right? But that would never deliver the transition state for the dihedral angle, favored dihedral angle, to do room temperature 0 degree CH activation. What happened is this. Although we got a crystal structure, just as John got, but we think that's that's the major species, but not reactive. The minor crystal structure, finally we were able to obtain recently in 0 degree was this one. The imidate was formed by deprotonation, and the imidate was mimic the carboxy acid chemistry to position the palladium in the same dihedral angle fix. So in the end, it was the same chemistry as the carboxy acid, and that's why we can do the CH activation at room temperature for sp3. Okay, and we have another limitation. Once we published that, we realized there was another huge limitation. That is, we can only do primary CH bond. We cannot selectively hit the methylene CH bond. That's another big problem. What's the problem? If you look into the literature, as long as you have a phosphine or dipyridine, you can do methylene. So why we could not do it? If you look at Dagula's beautiful chemistry using this very strong bistante chemistry, you can do it. And ourselves also did it using this pyridine. But you can't use Evans auxiliary potentially to do methylene CH activation. Why that is the case? And of course, we screen, we design ligands, and nothing happened. Finally, there's one interesting story, I will keep it very brief, was George Dryside once came to Cambridge to visit, and he asked the whole faculty, what's the most important thing in the question in chemistry? And nobody answered, of course, as usual. And he finally replied after 20 minutes of silence, he said, delta G, delta H, and delta S. And honestly, I thought he was joking, he really can't be serious. But 10 years later, I realized that I remember that story, and it turns out that is very important to think about, because if we need a strong coordination in the first step, and that is for the sake of entropy, then we are in trouble. Because then we always need the pyridine to be in the molecule, in the substrate, to assemble the entropy. But what about if we were all wrong in all those years? We don't need it. What we needed is a weak coordination, as I already maybe showed you in sp2CH activation. What the pyridine is doing maybe is enthalpy. If it's enthalpy, then we don't need it to be installed in the auxiliary. We could design a ligand to influence from outside to drop them down. And if we use weak coordination, the ground state is also more reactive, because the strong coordination also brings the ground state down. So basically you have a double gain if we can develop that idea. So that was the idea, and it turns out that indeed works. Okay. Finally, we came up with this ligand using this Evans auxiliary, I would call, for tonight at least, and then we can actually do the methylene CH activation. Okay, to control ligand control. Without ligand, no reaction. Okay, and you might ask, what took us so long to develop this ligand? As I already hinted, it's not easy to come up with a ligand in CH activation. Why? Even though we knew we need a lot of electron density to pump into the palladium by doing the enthalpy compensation. But the question is, how do you avoid this structure? You have this two strong ligand coordinate palladium, and that will avoid the subject coordination. You can never do CH activation. So what we did is to maintain the coordination, but ensure the steric repulsion from remote distance. If the second ligand comes into coordinate, they will start to really have mutual repulsive. Basically what happened is, these two ligands really hate each other. They like palladium, but they don't like each other. So they repulsively kick the one out, and you can follow this beautifully by NMR. You can only have this crystal structure. By the way, we have a crystal structure, and at 0 degree only, and you warm up to room temperature, this guy came off, and the substrate come in. You can see NMR structure, and the dihedral angle assembled. Everything is perfect. CH activation happened. So let me finally finishing by showing you one synthetic application that is enormously important at the moment to BMS drug discovery project for peptide drug synthesis, okay? And let me explain to you what's the problem. The problem is you want to start with the cheap and simplest chiral molecule amino acid and make hundreds of unique library chiral amino acid. So finally we developed one ligand that can do one chemistry, arylation. That's great. With this auxiliary, very easy to remove. We can scale this up to 10 gram scale in the lab routinely. We then developed another ligand that can selectively insert into the methylene CH bond. So you need two ligands to control, one for primary, one for methylene. Now we're in business. We can, this is the subject table you don't need to really go through. Just to tell you, very easy, broad subject scope. But let me show you, this is a magic scheme for us. By taking this this simple aniline, we can, in one part, sequentially add two ligands, control the diester selectivity up to 50 to 1. And I always believe the diester selectivity is still very powerful tool. It's just so reliable. And you can make this chiral center very hard to make. You may wonder, can you make by hydrogenation? Actually, very difficult. Why? Because it's very hard to make that double bond as cis and trans to control the double bond geometry and do that hydrogenation. Even with Andrew Fowler's catalyst you can isomerize as well when you do the hydrogenation. And the beauty, of course, is by simply switching the order of the coupling partner, you can access both diacetyl, like Eric Coretta, the beautiful chemistry, divergent. In NTO, both chiral center you can access by simply changing the coupling partner, of course. So that is very good. And if you think about this ligand, that is a very interesting ligand, right? Almost like Evans copper chemistry you could stick in here. But now we suddenly made not only the steric bulkiness, but we can also study how this remote chiral center can perturb the transition state of many, many reactions in our lab. Because that, for the first time, allows us to introduce another additional center to the oxalosyl ligand. And we are very excited to make a library of this and to test the chemistry. And the final slide of chemistry, just to show you the distance is the same. In the very beginning, I told you we want to control the distance. Now, by designing a new ligand, we were able to control the distance, remote sp3 CH activation as well. And our dream is to do one more carbon, then that's it. We don't need it too far, because as I told you already, it's only R, beta, gamma, and delta. That's all we care about. And you can also do different transformation, not just arylation. You can also do olefination. And that's amazing transformation. If you're familiar with Hecker reaction, even Hecker reaction cannot do the intermolecular transformation. The best chemistry was published, we are inspired actually, by Greg Fu. It's intramolecular sp3 Hecker reaction. But intermolecular Heck is very difficult. But now by doing this ligand, by doing the intermolecular coupling, you can do it. And I have to confess, the catalysis is not great. We cannot use air at the moment for this catalysis. But I'm sure this is just a beginning. We will continue to work on it. And hopefully, eventually, we will deliver the catalysis, a better catalysis as well. And finally, I just want to summarize what I have told you. If you fall asleep, now you can wake up and let me tell you all you need to know is two messages. Number one is the second step of the diagram. We have really exploited the weak coordination is really sufficient and even better in catalysis. And the second diagram showed you the first step is very crucial also to use a weak coordination. In best scenario, we were able to use Evans auxiliary and the ligand to accelerate this transition state, to deliver a wide range of CH transformations. And that indeed, and we can control enantiomer selectivity as well with many, many sp3 CH bond cases we are also reporting very soon. And finally, but the most important slide is to thank actually, this should update. I have many students coming. They are not on the list. But let me thank all the group members in my lab. I can never thank them enough, really. Every time when I mention them, I feel my tears is going to come in. It's a wonderful group of people. It's just full dedication, very passionate. You can discuss them anytime. 1 o'clock in the morning, you can discuss them with chemistry. Of course, only if they want to be there. And of course, I have to thank all the funding agency, and I always want to acknowledge, because it's a special occasion, I want to acknowledge Royal Society in 2003 for funding me that proposal that I wrote in Harvard, because at that time, I had very little data. But they were very generous. They funded that proposal, although I didn't finish that grants. But of course, I have to thank many, many other funding agencies as well. And I am very grateful to the NSF Center as well for collaboration with many, many people. Justin DuBois, Hugh Davis, and just some of the very exciting people to collaborate in the center, okay? And of course, the industry, I have great collaborator from Novartis, Eli Lilly, not Amgen yet, but BMS and Vertex. We were just doing that. And Syngenta as well. And finally, thank you so much and congratulations to Professor Evans again. And I really want to take this opportunity to say a big thank you to you from all of my group for inspiration to our chemistry. Thank you so much.
Wow. I doubt very much that anybody's asleep or tired or lacking energy at all. If there are questions, please identify yourself, and I'm sure Professor Yu would be happy to entertain them. I had a general question. If
Thank you for asking.
Well, with the one of the real powers of the methodology seems that it's the ability to use simple functional groups for directing and what have you, and you showed so many different possible combinations of substrates and coupling partners and what have you. But I wonder if there's concern at all, or if you looked into competition studies for the opportunity of redundancy of certain functional groups, or the different competitions between sites.
That's something we definitely are doing it on the way. We call it, it's a full paper coming as a hierarchy of the coordination power. Okay. So it's from strong to weak, and basically we are trying to establish the strong one we are going to abandon. So we're going to try to tune the moderate and the weak, and definitely you still have the most powerful direction is still the amide. So then it goes down to to carboxylic acid, then it goes down to 1-amide, and then hydroxyl, and then ketone, and then ether. So we have all the data, and then we will write a full paper to provide a guidance as a hierarchy of directing power.
Hi, Jin Quan. Carmen Dral, Chemical and Engineering News. So the guiding principles that you talk about, weak coordination, ligand acceleration, those are sort of unifying throughout your research. But as you have said, the structures themselves that have been used throughout are rather different depending on the cases. Maybe with time, and this is maybe a philosophical question, how similar do you think you could, or how universal do you think you might get these things?
I think it's very hard to be completely universal. So the realistic hope is the carboxylic acid will all be this amide auxiliary. And we will make the auxiliary readily available and very cheap, and we continue developing new method to remove it. So actually, we just developed a new method through radical to remove that amide at a room temperature. It has to be very practical, as I said, just like Evans auxiliary. So that's for carboxylic acid. I believe there was a long-term future for using that auxiliary and have ligand. And the coordinated structure is always like that. We knew that. And then I guess you're saying is for ether, for hydroxyl, they are sp3 directing. The atom is, the lone pair is sp3. And there, the ligand tuning is a little bit different in terms of conformation. So I guess we can write a paper then summarize how do we develop ligands for the alcohol and for the amine. Actually, they are very similar. The amine and alcohol are very similar. We have the enantiomer selectivity, as you can see with amines and with hydroxyl. Both use the same ligand backbone. So they do have a lot of similarity. So if we are not ambitious enough, we're happy to do carboxylic acid, amine, and alcohol, and ether probably. Then we will separate them and then have different ligands to provide guidance for medicinal chemists to use, I guess.
Kit for the biologists.
Yeah.
Thanks.
I have a question up here. Hi, I'm Jana Markley. I work for Paul Hansen at the University of Kansas. Very impressive talk. I don't know if I should start preparing a postdoctoral application or start performing.
Please.
But I had a question. So in a system where you have symmetric, like biaryl system, could you use chirality to generate a single H-rip isomer with your CH?
Yeah, that's very interesting. Actually, I was talking in an SES meeting, and an undergraduate heard my talk, and he proposed that idea. Then I told, why don't you come here to work? And he's arriving tomorrow in Swiss to working on that idea. It's atropic, like biphenyl tried to do a lactonization, and he even selected a natural product. His name is Marcus Farmer. Remember that name? It's a real story. He proposed that, he sent to me, it's all his idea. And he wanted to do exactly what he said. And he has a natural product in mind as well. It's quite amazing. I mean, he's from South Florida, first year undergraduate.
Let's thank Professor Yu once again.